What is radiant energy? If you're talking about radiant energy, to me, what do I consider radiant? Okay, what I consider radiant is the capturing of a spike. I consider that radiant. You know, anything that, say, I generate the radiant energy. I do that by my coils, my switching circuits. That's how I generate radiant energy. In other words, what I'm saying is that I'm only concerned with a sharp transient in the spike as far as the radiant goes. You know, as far as negative energy goes, the negative energy comes from the battery. Once I generate this sharp transient and charge the battery, it's a negative effect to the battery because there's no heating of the battery with the radiant charger. So basically, the thing is to build circuits that generate these sharp transients and then steal that sharp transient and put that to the battery. That way I don't need much current at all to do it. Next question.
Could you talk a bit about the radiant spikes that we saw on the screen for the pendulum oscillator?
The radiant spike, the pendulum's a totally different machine. You know, and it's like one transient spike at a time. You know, it's still the same principle. It's still, each time that the pendulum goes up or the pendulum goes down, we just transfer that energy from one, right, it's a balancing act between, you know, the pendulum movement. And so one battery being lower than the other battery, it balances between the two batteries. And it's still the same wave, except that the wave it's much longer in time.
What happens if you try to swap the primary battery with a secondary battery that's being charged with the radiant?
No, you cannot. You can't mix the two sources. One electricity is completely different than the next. One, you're asking, you're putting in a positive form of energy, right? And you're asking for a negative form out, which is the radiant. And so therefore you can't just swap the batteries without a time period between them. And you just can't take the back battery and put it on the front battery because it's just going to kill itself if you do that. However, you can put as many batteries as you want on the back. Now you can move that to something else. You take the battery that you charge and run an inverter, and then you could run the inverter and charge the front battery. So you have to change the forms of energy because they're both different forms.
So that would apply to every one of your devices?
Every one of my devices.
In a normal circuit, when you increase the load, the current increases. What goes on in your circuits?
You're talking about Lenz's law. You're talking about the back EMF interfering with the work of the motor. It's free in the monopole system. We don't even have a Lenz's law. You know, we have no counter back EMF to slow down the motor under load. So if we slow down the motor, we can't draw more current. We never, you know, the current is just going to go down. Motor's going to go slower, same pulse, same spike's going to appear, same radiant. But we're not faced with a Lenz's law problem, you know, of counter electromagnetic force.
Is the pendulum system a closed loop system?
No, they were two separate loops. There were two separate loops, one being closed at the back and one being closed at the front. But the two loops are not tied together, and it's out of phase from each other. So when the front's doing something, the back isn't receiving a signal at all. It's not until the pendulum swings the other direction.
So you had so when the pendulum comes down, the trigger pulse comes in.
Well, no, it comes in after. You got to charge the iron in the pendulum, and then the trigger pulse takes place later. About 22 degrees after that.
In that motor behind you, you were talking about an imaginary south pole. Could you elaborate a little bit on that?
It's an imaginary pole between the two magnetic norths. Because remember, these are sharp pinpoint beams, and so they come up and they go around. And then, of course, the south appears, and you can see that you can see it with a magnetic indicator, that between these poles, right in here, the motor isn't running until it's past the pole. Between the two north poles is an imaginary south. And so, being that this thing comes around and gets triggered, gets triggered here, see, when it passes the trigger circuit, right, it's always past the trigger circuit by about 22 degrees. And so it's really in between these two magnets when the coil fires. So, it's just imaginary. It's like, it's a scalar sound. You can see it with a magnetic indicator. It shows up, but there's no magnetic pole there. It's where the fields all come together, not a plastic wheel. See, actually, this shaft is south. Now, if the magnet's way up here, and there's a loss, how did this get to be south? Because this is a real south pole on the shaft. And then, of course, coming out, you have the north pole going up, comes around, right? But this actually becomes, and remember we talked about the magnetic beam being pinpoint on each one of these. So it's pinpoint. And then in between here is the south scalar. These are all north poles together. So these are pushed together to make up a magnetic pinpoint beam. So it's not a good generator. So it has trouble getting triggered, when you spin this thing. But I don't know if you can hear this or not. If we get this thing to... Those are the triggers. And see, it's always triggered after the fact. There's only one trigger. So. And it's more like a big radial magneto. Because the H waves are involved in this too. And of course, the light you see in the background is being generated from the trigger, just from these scalar norths. Because there's no south pole involved. It's imaginary here. And that's what's driving the engine. Take away the magneto, and it'll just, no power at all. So it's not generating a thing. Notice there's no drag on it even though it's connected to the battery. There's no back EMF.
So there was a piece of the footage that I saw about, I think you were demonstrating the magnetic monopole motor to William and showing him 2 banks of batteries there, and you were talking about flip-flopping, but I'm going to kind of miss that impression because I think you're saying that you
Can't trade them.
You can't trade them at all. So yeah, it was about just making clear that none of your devices can be used to flip-flop batteries.
No, you wouldn't want to flip the batteries. It's two different types of energy. One energy is driving the system. The other one's a radiant type energy being put into the secondary battery. Now, you can drive normal stuff with it. You can drive a light bulb, you can drive an inverter, drive a DC motor, you can drive an inverter to charge the front battery as long as you keep the two electricities isolated. See, the battery performs giving you the same thing, but for some strange reason, if you trade batteries back and forth, you just run out of energy. However, if you take a little bit of the back battery and use an inverter, you can charge the front battery. You have to change the form of it.
So if you took an inverter, you could swap back and forth?
Yeah, you could.
That motor behind you, what does that have in common with your other motors?
They all remain the same no matter what size they are. They all function absolutely the same. There's a smaller one over there, then there's another one, then there's one over here, there's one in this corner over here. And you see just the sizes have changed, although they operate identically the same.
So in terms of their ability to restore badly corroded batteries, there's no difference?
Right, that's the radiant charger. That, the motor, yeah, you can notice the same thing. You can, because since these are such high voltage unit, they just can charge a battery that's been sulfated. Actually breaks the sulfation away.
So the radiant energy can restore a scrap heap battery that's completely sulfated?
Yes, it does. Breaks it off.
Does the number of poles on the different models of motors make any difference to their effectiveness, John?
Doesn't make any difference. Could be 2 poles. Could be 1 pole.
And in the context of your radiant charging machines, how do you see the term COP applying?
Well, the COP is completely different from what you're measuring. One doesn't have anything to do with the other. I have to go along with Tom Bearden on that most people can't measure COP. They have no idea what this machine's doing. And the COP is in the battery. Does the battery run longer? Does it take the charge better? Does it charge faster? You see, how long can we sustain this battery? You're building up the COP in the system by charging the battery with this type device. Because we're not saying any COP is developed in the machine whatsoever. It's all in the chemical, in the battery. You can charge with this system, and immediately when you load the battery, you're going to find out that it's extended. Now you start calculating your COP, because you know what the battery can put out. You do that, and everybody likes the favorite thing, joules. And but you know that if you charge this battery and you put this in, but then you get extended out, where you know that under a normal conventional charger you're losing time each time. This system gains time each time, and it gets to a certain point, and that's it. That's as efficient as the battery's going to get.
Tom talks about negative energy, and you talk about radiant energy. Could you expand on that a little bit?
They're both the same. They're one and the same. If you're talking about radiant energy, you're also talking about negative energy. It's basically the same thing. It's the negative end of it. I mean, a sharp transient produces this negative energy.
How do you see radiant energy coming in, John?
Well, it comes in waves. Radiant energy comes in waves. So, of course, you're going to see this alteration. Because all the devices are switching all at the same time. They're all at the same level. But yet you see this rolling wave that's low in frequency. So you see this sort of like ocean wave. Sometimes it's higher, sometimes it's lower. This is nothing more than what Murray talked about, or any of these people, about the way they said that the energy comes in waves. It seems to be like an ocean wave or a gravitational wave. It seems to ride in on some form of gravity wave, where it's up and down and up and down and up and down. Sometimes it comes in stronger, and sometimes it comes in a lot lighter. Well, it does change. This wave does change during, say, a full moon. Some of these motors have been known during a full moon to speed up just a little bit. They actually go a little bit faster at night and a little bit slower during the day. And of course, we've been able to see this on RPM gauges and things like that, that these things actually run a little bit faster at night. So I wouldn't really say full moon, but...
Who was the first person to really stumble into radiant energy? Was this Stubblefield or Tesla?
Tesla.
Yeah.
Tesla's the one that basically, did everything radiant. And Stubblefield used it too, but a different form of it. So it's just something that, people are trying to duplicate to this day. But we've found a way to do this, and we just charge batteries with it.
According to Tom, eventually there might be a possibility of running a huge charger output on secondary batteries that could power houses or whatever from just a tiny...
Well, yeah, if you look at a Tesla coil, when a Tesla coil's operating, you think that the sparks that are being emitted from it are actually coming from, but actually it's drawing this in. It's more like a fluid, and providing that you get this thing really into resonance and stuff like that, this actually grows. This, envelops a whole field with this gaseous mixture of white, which is actually what you have to convert to get the energy, from the vacuum. You have to be able to convert this radiant. You have to be able to translate this. To translate this in some form, and then turn it to something that's usable, like what we know as electricity. But then once again, you're going to end up charging a battery with it, or you're going to end up running lights with it, or you're going to end up running a DC motor with it. Now just using this stuff right off, you're not going to run an AC motor. But you're going to run an incandescent light.
Could you talk about the nature of the radiant energy being a little bit more like a gas? Not like a conventional current, but like a nebulous gas?
Yeah, Tom talks about powering a battleship with a flashlight battery, which is entirely possible because we've seen some of these oscillators run down to 0.4 of a volt. We've seen these things run on moonlight. So we've seen them go down, so we know at 1 volt they're putting out a half amp or something like that. So, yeah, it's entirely possible.
So let me make sure I understand this. The system you're talking about would be the one that you currently have in development.
The system that's our proprietary system, yeah. And I have to put that in there, Tony, proprietary system. I'm not going to talk much about that.
That's pretty much all my questions.
So we're done. Now I can take this microphone off.
We're just getting going. The book that you have now with Tom Bearden, what have you put in the book, John?
I've let loose all the inverted circuits Tom and I worked on to prove out what this stuff is. This is on a very minute scale, so people can actually make a working circuit. So Tom and I were happy to let that go into the public domain because we want people to work on this. So they have no excuses anymore. You just get the circuit, make the circuit, don't change anything, and study what it's doing, how it operates. And that's my suggestion to everybody, is just time to get to work. Don't change anything. Don't think that you know anything better right at this moment in time, because you don't. It's you want the circuit to operate just like I said what's there. And then after that, after you get it working, you can make all the changes you want. But up until that point in time, if you make changes, don't expect it to work until you really know what this pulse is and what's going on with these inverted circuits and how the battery is being charged from the inverted circuit.
And the first book, which is also being reprinted, the one from 1984, several people took that and...
Yeah, several people, right, the Bedini's free energy generator. Right. I think even Mythbusters tried to build that one, didn't they? But yeah, anybody that follows that book, I would suggest that they follow it precisely, that they build it just like the diagram in the back, and get it to go first. You can build a solid state relay that does the switching like Watson did. But just expect that if you start running stuff with this, you'll probably disappear too. That's it. I mean, Watson's machine was like an 800-pound flywheel, and probably was 15 to 18 feet long. Probably weighed something like almost 1,500 pounds, right? And did something like 5 kVA. And was running on 2 small little car batteries. And we're talking about a big mass, we're talking about, you know, an aircraft starter that he had to order special, right? But once he wound up this flywheel to, I guess it was around maybe 400 or 500 RPMs, then he only had to supply a pulse every once in a while. Click, clack, click, clack. Capacitor charges up, dumps to the battery. Capacitor charges up, dumps to the battery. Same thing as a monopole motor now. Only see, we tried to reduce the size of it so you could understand the effect of it. This is regauging.
Right.
This is regauging itself. So the 0 is in the center here.
Right. When you say regaging, it was basically changing.
Right, let's do this because everybody's always said to me, well, I can't find the South Pole. Where is it? Did you get that on film there, Tony? I can't find the South Pole.
That's the stuff.
It's not balanced.
You're just proving that the wheel's not balanced.
And that there's a rock inside the
There's
bear.
a rock in the bear.
Okay. Yeah. The professor must have his glasses. So. Okay. So see, there's a north. Are you getting this, Tony?
Yep.
Here's the north. And then you move out here and see here's the imaginary south at about 23 degrees right here. And this is, since the motor's attractive, it's going to push away on this south when it fires. So then you come down here and there's the north. See, and there's in between the south and the north is a 0. And then there's the south again. And there's a 0 between the north and the south. See, there's imaginary south there. And then there's a north. All right, so there's an imaginary south here and a null out or a 0.
There's the 0.
And a 0 again. And then a north. And then an imaginary south, a 0 and a 0. So there's like 4. What it's doing is coming around here like this, going like this, back to this one over here. So now what we want to do is these are all north poles. You can see by the indicator that they're just all north. There's no south poles out here. And what we're going to do is show you by just the little trigger signal. And when these blink, that's the spike that you want to capture. So we'll let it pick up speed, and it'll pick up speed automatically. It's pulling a lot of weight right now. So. Okay, but we're going to map these fields right now. Okay, so what we have is a north pole here, and a north here. So we have a south that does this. And then what we have is a 0 here and a 0 here. So we have this all the way around the wheel, like this. So now if we want to collect, the motor's pushing away at 23 degrees. This is actually at 23 degrees. Okay, so now we're going to run on the south. We're going to charge the iron with the north, and we're going to run on the south. So once again, this is the radiant energy we're going to collect. And you can see these things are burnt black from trying to contain that voltage. So here, now the radiant goes away and gets into the capacitor. And then what we're going to do is store this charge and then discharge it across the battery. So this is what we're going to end up with. Each time. And we're going to take another flash of that. So once again, we're storing the radiant charge in this capacitor. Gets to a certain level, we want to discharge it to the battery. And each time the battery gets that discharge, this is what it gets. Got it?
So the potential you're getting across that capacitor is what, about 400 volts?
Yeah, about 100. This capacitor is probably about 75 or 80 volts here with this capacitance. If you were to use this 0.1, it'd be like a 400 volts or 500 volts. Much more than what this capacitor could take. So basically, what you're going to do is you're going to store the charge, and you're going to repeat this operation over and over like this. Oh, let me get it over here. See, and then you time it so that you just give it that little arc right there. So it'd be about 2 or 3 seconds each pulse. So you just need to be over the battery with this pulse like this. So we did away with the capacitor. Because of the way this arrangement is, and we just go right to the next battery and it absorbs the radiant energy.
That's a 12-volt battery.
Yeah. See, this battery didn't have very much in it because it rose up at the beginning and lowered the impedance, and now it's putting the charge to the battery. As the battery falls downward, the impedance gets lower and lower and lower. So the energy is actually getting absorbed into the chemical right now. Do you want to repeat that again, Tony?
As well.
Okay. So we'll watch the capacitor build this time, and you decide which one you want. So we're starting out with a capacitor that really doesn't have that in it, a little bit. But see, they charge themselves after they've been sitting. Once they're charged under this method. See, so we've got this capacitor at 0. You can see it here. And watch, it's just going to build its charge up.
And that's just having one terminal connected.
Yeah. The other one isn't. Okay, so now we're going to connect it up and take this radiant energy. Let's take this one. Let's get some radiant energy here, and now we're going to just switch the currents. Okay, so here we go. So this is what we've collected. So now, let's not use a capacitor. Let's just tell the machine to charge the battery. We're going to say in this demonstration that the battery is actually the radiant collector. So you can see the radiant energy is on there full. So now we're going to connect this up. The radiant's absorbed by the battery. And we're just going to go ahead and push that battery up. So now we've traded batteries. The battery that we've charged, we now have driving the input. And the battery that's discharged, we're not charging. You can see it changing here with that pulse. So if we,
In effect, you're using, say, about 2% of the source battery, and you can
Yeah.
charge it dead.
yeah, that's what I'm doing right now, right? So to show you that it's not generating anything with this movement, we disconnect the source battery. And so it's not a generator. Now we trigger the radiant out with this pulse. And we're doing the mechanical work and charging the battery. We're doing this mechanical work here. And so you have to take into account the electrical energy in, the electrical energy out, and the amount of work that the wheel's doing to keep that fan going.
It almost seems to me like it's that mechanical motion is needed almost as a byproduct to get an action to trick out.
Yes, exactly, to get the triggering each time in the coil. And see, it's speeding up. As the impedance changes in the battery, it's starting to speed up more and more and more. Kind of interesting, isn't it? So this battery now is coming up, see? It's almost at 1350. Yeah. It's bouncing between 4 and 5 there, see? 9. Each one of those pulses is a little bit different.
You only had that on the capacitor for what, a few seconds?
Yeah. About less than, we want to discharge this capacitor. And then the other thing is don't leave the capacitors open because they sometimes build another charge.
Do you notice that they build their charge when they're near to these machines?
Oh, no. Just after we use them, sometimes they build up another charge, and we think that's the residual left over in the plates as they expand back.
So what you collected there in discharge was purely radiant energy?
Purely radiant. We transformed that high voltage into the capacitor, and then of course we get regular electricity when we short this out. We get real current flow. So when the battery sees real current flow, it just jumps. All right, so the idea is to not have this capacitor because this causes then heat in the battery. And what we want to do is take advantage of these high voltage spikes you see here. So you can see here that the meter can't even measure it. Doesn't want to measure it. It's got it locked. See?
That change in the noise that you're hearing when you took it off is that's just the lights.
You're hearing the high voltage being triggered. Now listen. That's these pulses. That's the magneto effect. So you remember that this machine works. Let me get this a little bit in the camera. Then what happens is this magnet comes down here and the iron charges. It becomes the same as the magnet. Now the magnet pulls away and the magnetic field discharges. That then is at the correct sign to trigger the devices. You can see it here in one pulse. See if we can get it. There. Okay. See? I'm not quite quick enough, but see there? It's after the magnet leaves.
So that's when it reaches the zero.
Yeah, that's when it reaches the zero, and if we take these LEDs, they're in two different phases here, and we just go across the coil. Okay? In other words, put the LED across the coil. And suppose we had a timing mark in the center here. So let's say that we can do something like that, where we can get close. You can see right away that the red one and the green one's flashing. but they're out of phase from each other. So if you get it on there and you hit the mark, it's a black mark, and actually we need a white piece of tape, but you'll find out that this will show you the timing if you look in here. You see the two bars in here? That's the timing. See, it's after the fact. It's after the magnet already leaves. So it's got to be running on a scalar sound, the imaginary pole. So if we put a white dot, let's just get a white piece of let's just say we had this white piece of paper, right? And actually it has to be much thinner than that. So if we put this in the center of the magnet, right? So it looks like there it is there. So it's right there on the green. It's after the pole piece. See, and so you can make a simple set of timing lights by using two LEDs back to back and a couple of resistors so that you can see the firing across the coil, and you can see it here. You can see one is the charge and one is the discharge. So that's one way you can do it, to find the exact timing. So what it looks like is that when this white piece comes around, that's the center of the pole, that it comes in, it charges the iron, it discharges and fires right about there. So that puts, basically, if we look at this, these zeros is basically where it's firing. You follow me? Then it it's in repulsion because it's already past it. So it's actually firing at 23 degrees, charging, discharging, firing. Follow me? Charge, time and charge, time and discharge of the iron, and then the pole is in repulsion, and then the motor spins. So that's exactly how this is operating. Got it, boss?
So if you could talk about the conventional uses of potential, and for example, conventionalists will tell you how you can use a battery and how you can't use a battery,
Right.
How you have to add them together and how you can't, and how it will or won't work in those ways.
Okay, so let's just look at it with these three batteries off the start. So here's what we have. We have this battery, which if we put these two together, we get 3 volts. And of course the positives at the top, negatives at the bottom. Okay? And we only have one battery on this side, and this is what we have. So we have one like this, and one like this, and one like this. So we have another battery, negative terminals at the bottom. This is the way I see differentials. All right? And these are both positive terminals. Okay, so if I said to you, okay, hook up the batteries this way, what would you basically say was there? You would say there was nothing there, right? because there can't be anything.
Right.
But there is. If we look at it, there's a potential that's flowing of 1.5 volts,
Right.
positive.
So in essence,
because-
what you're saying is that the
Right, so if we look at it this way, we look at a wave of 3, and we keep it in the same phase, and we look at a wave of 1.5. Well, that equals 1.5. Okay, now if we have a wave that's 3, and a wave that's 3, plus and minus, they're in the same relationship. So we've altered the frame. We've taken this wave and we've moved this frame underneath this frame.
right.
So basically what we're looking at is this,
Okay.
okay? And this equals 0.
So you can have hidden information and a zero.
Yes, you can have hidden information because I could take this wave and expand that wave and expand that wave, and I can then put information in here. Right?
Right.
And then see this 0, when it zeroes out, is going to equal, this 0 is going to contain all this information in
On
it,
the substructure.
all the substructure. So that's the way I see differential equations in what I do with my circuits. So if I say to you, okay, I have a transistor here, all right, and I put this wave in it, and I take this portion, right, and I take this portion, and say that these are equal. I'm putting this information in the device. But what's coming out of this end is just the scalar function,
The
which is
substructure,
this,
which
which
is
is going to look like this.
Right. So what you're saying is that's all of the substructure. You send in this wave, you pick off the substructure which is in the zero, which is carried along with that wave.
Right.
And that's what you're picking up.
So suppose we did a sophisticated circuit and there was a device here, and there was a device here, there's a device here. And I pick off all these structures. A, B, and C. Okay, and they both have similar structures, right? And that all, I decide that I don't want to form a zero. I just want the potential.
Right, right.
So what I do is I take this A and I go A plus B plus C equals
Whatever.
some number, right? All right? And then suppose I don't like this number. Suppose this number is 3. And I say, okay, now what I'll do is I'll take this last potential and I'll take this phase and beat it against this phase and get 2.5.
Okay.
Because the way that's going to work is if I have this potential that's 3 and this potential that's 2, what I have out here is 1,
Right, right.
along with the 0. Because it's trying to cancel out, but there's this difference in potential. It's the same thing as if you took this battery. So when we talk about inverted circuits, in the book and stuff that's coming out.
Right.
If I have this potential generated with a spike, and this is 300 volts, so we'll just call it a spike, right? And I put this 300 volts to the plus, and I take and invert the transistor to the ground, right? And I come up with some form of switch here. When I close that switch, the difference in potential is across this battery.
Right.
So if this is 12 volts, this is subtract this 300 volts,
Right.
and that's the difference in potential that's charging the battery.
It's across the battery.
So we want just potential and no current.
Right. So in essence, what you're saying here is two things. First of all, you're trying to get rid of the mathematics involved in current because you're not
Right,
interested in
right,
it.
I'm not interested in it.
And the second thing you're trying to do, you're talking about a sort of hidden
Variables.
variable just to do with the potential difference and the hidden substructure within potential zeros.
Right. See, the whole idea is to hide all the information in the zero.
Right.
So this becomes a sharp transient. It becomes a very sharp, just transient. And so if we really expand that transient out, what we have is all this hidden stuff inside the zero.
Okay. And that's an expansion of the.
Yeah, that's an expansion of this.
Right. Okay.
And that's how I see the electronics working.
Right. Okay.
That's how I see the motor working. I say that you know, this wheel has a north pole, and these are all north, and we know, and so, but between these two norths is a zero, two zeros, and a south.
Right. Right.
See? So what I want the motor to do is I want it to give it the correct phase to fire. So that's the north. So what happens is the magnet comes by, and this field actually couples like this.
Right.
And this becomes energized.
Right. And this is the core of the coil.
Yeah, this is the core of the coil, right? And so I've charged this iron, and it's at this potential.
Right.
It's charged. Now the magnet leaves, right? And the iron wants to discharge, so it flips.
Right. Right.
And that's the correct phase for this transistor to fire, right? And then since it's an attractive motor, since it's in attraction instead of repulsion, what kicks the wheel away is this south.
Right.
That's imaginary. It's really there because you can see it with the magnetic indicator.
Right. Right.
And it's just enough. There's no power involved in the machine whatsoever. In other words, there's not any torque being developed.
Right.
It's just a triggering mechanism to catch this energy.
So in essence, what you're talking about is this south is a trigger to get the motion, but
Yeah.
what you're really getting at is coming back to what you're talking about, the hidden information in
Yes,
zeros.
yes.
It's when you pass the zero that you get this hidden
Yes.
information, which is dropping
I
through.
want to combine it into the spike and send that signal to the battery to tell it, recharge.
So in conventional circuits, that all gets chopped off.
Yes, in the conventional circuit, if they see that, they're going to short that out
Right, right.
to protect this device.
And that's shorted out across.
But since I'm taking it off, I'm just catching the spike and sending it to the battery. I don't have to protect anything.
Right, right.
If I want to protect this device, I'm just going to put a neon light here. I'm going to limit it to 90 volts.
Right, right.
And that's exactly the way I see it.
So the mathematics and the workings behind this is simply just down to difference of potentials, and that's all you really.
That's all I care about is the difference of potentials. I move one potential to either a higher level or a lower level.
So in essence, when you can kind of get confused by plus and minuses. Because
That's
it's
why I
simply
can
just-
use, right, that's why I can use two identical batteries, because I'm building up the potential to trick one.
Right, right,
See, there is no free lunch. You have to do the work to get it.
right. But once
Once you understand that fundamental, you can take all your electrical circuits and look at them as a differential and say, gee, I can take a little bit from here, I can take a little bit from here, and think about it. It's all in the same phase. It's all additive. Now I've got this high potential.
Yeah.
And if my potential is too high, I can direct another phase and subtract
Okay.
from the potential because it's out of phase by a lesser degree.
Right, right.
So in essence, I'm looking at a wave that may look like that.
Okay.
Or I'm looking at a wave that may look like that. Now what's the motor wave look like?
Okay. So this is your.
See, this is the actual battery level.
Mm-hmm.
And this little piece, when you see it on the scope that comes down, is in the negative range.
Right.
The device is going negative. It actually wants to become a negative resistor, or a negistor,
Right.
a
Okay.
transistor that's a negistor. So that cools it off.
Okay. Okay. Okay.
And that's just the way I see it. The motor wave, this is the battery level, and then the spike is here.
Oh, but what I mean is when you look at all the spikes together. the
Oh yeah,
piece-
yeah. You're seeing this.
That's right. That's right. Yeah.
So actually, what you're looking at is a digital signal. For somebody to build a receiver to pick up the background,
Look at the backgrounds.
that's a real fast device. That's like in the terahertz
Right.
and beyond.
So would you kind of say that? Because it seems to me, if you've got let's take an electromagnetic wave, so you've got a kind of field.
Yeah, right. Yeah.
So what you're really looking at is the kind of motion along here.
Yes.
The fretlands,
Yeah, but this one's longitudinal.
That's right. Yeah.
See, this is the EM, and this is the longitudinal.
Because what I was thinking about this, what I showed you, is you have that T field.
Yeah,
in the
okay.
longitudinal part, and you've got the normal magnetic field.
Right, right,
And that's the pressure part.
right. That's the pressure.
So I'm kind of thinking that that's the natural. These are kind of pressure
These
waves.
are pressure waves. So what you want to do is build a receiver that tunes into the pressure wave.
Right.
See, it's way beyond light because you have to catch the neutral particles.
Mm.
Then you have to convert them into something
Yeah.
to turn them into electrons
Right.
because everything you do is electrons.
So in essence, everything that's like a particle nature belongs to the transverse, and this gas is the pressure part.
Yeah.
Right.
It was short, but that's what it's done.
Suddenly everything becomes clear.
Yeah, because once this light bulb turns on,
Yeah.
you'll never forget this light bulb.
Right.
You'll walk around and say, you know what? I've seen some bullshit in my life, but this takes the cake
Yeah.
because this is actually simplicity. This is like saying I have two trees. Do it yourself. Do the measurement yourself. I have two trees. I have one tree here and one tree here. One's a small tree and one's a big tree.
Yeah.
What's the potential difference between the two trees?
Right.
Well, if you stick a meter in there, you're going to find out. It's a noise.
Yeah.
Nature's full of these potential differences, and they're nonlinear. So guess what? You can't have linear math.
Right.
You have to have nonlinear math.
Right.
This is nonlinear. That isn't a linear signal. You know, what comes out of all this is a nonlinear zero.
That explains it really well.
Yeah, you need a nonlinear math.
My work cut out for me.
You do. You're gonna get it.
Yeah.
You know, you're gonna sit down in the chair and say the guy's a madman. That's all there is to it. He's a madman, but he showed me how to make this little motor, and it's operating and it's charging this better. Now I want to know why. I want to know why, because it goes against all contrary laws. You can't have a 12-volt battery charge a 12-volt battery. You can divide the charge between them. You can suck them both dry. But you can't have one that's lower than the 12-volt battery charging a 12-volt battery.
Well, I guess, I mean, in other words to say, it's probably best to say that in terms of, whenever you talk about a conventional circuit, you talk about the current flow, we use that, we measure that, that's something we can quantify. But in essence, the current is just simply a sort of back reaction to your
Yes.
dipole is disappearing.
The dipole is destroyed by the current.
So
As long as you don't touch this,
right.
this dipole stays. So if every once in a while you want to touch this, right, and you just go, the current didn't have any time to get there. See, this is probably drawing a lot more current than can be measured, except it's so fast, it's instantaneous, that you can't destroy the dipole that quickly. The idea is to make the dipole last as long as you can last and get the most work out of it.
So I guess in a way you could say there's like with all this substructure, there's a hidden way to look at information and voltage flow, but in terms of when you get rid of the currents, that's what you're left with, and you don't want to use the current because that's destroying everything you're trying to get at.
Right. Yeah, you see, if the meter sees a zero, you can't measure the current.
Right.
So therefore, how does the battery charge if you're not measuring the real current?
So you could kind of think of a current as kind of, and everywhere in nature you see that whenever you impose some kind of change or differential, it always tries to balance itself out and make itself balance. And in this way, it seems like current is what happens to do that. So if you're interested in...
Well, the current slows down. What controls everything is the magnetic field.
Right.
So the bigger the magnetic field, the slower the radiant. It's like a pressure valve for the radiant.
Okay.
You follow me?
Yeah.
The electromagnetic field, the normal field, is just a regulator to keep everything from going pop.
Right. Okay.
You see, in our experiments with the radiant transformer, you have, if you lay out the wire on the ground, say you took this motor wire,
right.
you laid it out on the ground, it'd want to oscillate at some unnatural frequency,
Right.
and there's nothing to slow it down, so the device can't go that fast.
Right.
So what do? You take the wire and you start to coil it up and coil it up and coil it up, and pretty soon the frequency slows down
Right.
because the magnetic field is collapsing inward, slowing the frequency down.
Right.
So now, with that frequency, only a few of these radiant sparks are able to get through. But that's enough.
Right. Okay.
So if you come up with some device that can go that fast, you could just have a straight wire in front of you, and it would output everything that's in the heaviside field.
Right. Is that similar to what a Litz wire does in a way?
No, a Litz wire contains the magnetic field in itself.
Oh, I see. Okay.
So what you want to do is when you use these, right, we're talking about just one straight wire.
Right. Right.
And we're talking about this flashlight battery at this end.
Okay. Okay.
So if we cause a pulse on this one straight wire,
Mhm.
and we had a device that was fast enough
Right.
to switch that fast,
Yeah.
you could capture everything around that wire because the frequency would be so high.
Right. Right.
See, it'd be off the scale in voltage.
Mm-hmm. Okay.
That's what we're talking about.
Right.
We just found a way to slow it down through a magnetic trigger.
Okay.
All right?
Okay.
And by coiling up our transformers and stuff in these coils, we're just slowing it down.
Mm-hmm.
We're more than satisfied to get, 60 pulses a minute of this stuff.
Right.
That's all we need for the battery.
But potentially there could be a huge amount of stuff that you're not getting, different design you could use.
Well, yeah, a huge amount of stuff like well, you didn't actually see it this afternoon, but like when they took those golf cart batteries after charging them, right? Normally they could only run 1 hour at 100 amps.
Right.
All right?
Mm-hmm.
These guys did 2.5 hours today. So where did that energy come from?
Right. Right.
What went into the battery
Mm.
that made it last 2.5 hours at 100 amps?
Right.
See, you have to take this. You have to take whatever's in the battery that's a frosted piece of glass,
Right. Right.
and you have to clear it up. So it's like a clear window pane.
Okay.
So in other words, there's no sulfation there. There's no fog on the plate.
Right.
So once you have the full access of the battery, it isn't dying. You
Right.
follow
And
me?
it just keeps that.
It's getting bigger. It's getting better. That fly's bugging me. Did you get all that?
Some of them. Because it really helped when you pulled the mic off.
It's fine because my
No, but, I mean,
Eventually I was able to read yeah, I got yeah. That's good.
you got it all.
There's a lot there too. I mean, this is so far away from conventional stuff. I can't even pick a conventional book up now thinking this is bollocks.
Well, now you understand where I've been for the last 30 years.
Yeah.
It started with beer.
Yeah.
Talk about bizarre.
Yeah.
Yeah.
Forget the fly. I told Rhonda I would be home tonight. Spent a long time doing that too.
Yeah. It's Victorian there.
Yeah. See, and I was just on the other side of this, down a little bit when
Okay.
I built the other house.
That was Victorian style too, wasn't it?
Was it Victorian? Rhonda actually designed that house.
Did she?
Mhm.